سلام. اليوم غنمشيو من لاديسيون الكوانتيك، ولكن قبل نعاود لكم عقلي في حصه كوانتيك. الدري اللي حدايا الصاط فهمتي شي حاجه؟ انا باينه صاحبي. شوف دابا البرا سكالير قريناها صاحبي، سكالير قريناها في الميكانيك، داكشي باين. وكات هو فيكتور فهمتي، كات هاد الجهه وبرا هاد الجهه، كل واحد شاه جهته. اذا جمعتيهم برودوي فيكتوريال صاحبي قريناه في هو في الميكانيك، يعني ماشي شي حاجه جديده غير تبدلات نوطاسيون صافي، يعني ماشي شي حاجه. ما سمعتيش بروف وقيله الدري اللي حدايا تكون وقيله عقلي عاوتاني ملي كيحاول يفهم. بالنسبه لهاد الرياكسيون لا اي رياكسيون كاللوحه، ارتاح ليا مع راحتك، تكا ليا مع راحتك. شي حاجه دخلت العقليه هذيك ما دخلت ماشي مشكل. ما تحاولش تفهم فهمتي، ما تحاولش تخدم بزاف عقلك، خلي داكشي يدوز فهمتي. كيما كتفرج في دوك الفيديوهات الاخرين اللي كتشد فيهم بزاف الوقت وانت فرحان، نفس هذا تتعامل مع نفسه. انا واحد الانسان كنحاول انا نفهم شنو كاين، شنو طاري في هذا العالم. شي حاجه دخلات هي ديك، ما دخلاتش صافي فهمتي، كدوز عندي حتى من بعد قد تجيني والله اعلم كيفاش تجيني وصافي. بحال هكا بغيتك تتعامل معايا تقريبا في كاع لي فيديو فهمتي. ارتاح، كون اليز فهمتي، ما تاخذش هادشي سيريوزمون. خاصني نفهم كلشي، او ماي غاد خاصني نوقت بزاف فهمتي. شويه عليك، حيت هذه الطريقه الوحيده باش هادشي يعجبك، حيت هادشي زوين الصراحه، ما نكذبش لك هادشي زوين. ولكن ما عندنا ما نديرو، خيبوه لينا الاساتذه. ما عرفتش علاش زعما بالضبط، علاش كيتخاد زعما هادشي سيريوزمون بزاف. هي عندها معنى، ولكن واخا هكاك ما عندهاش معنى بالنسبه ليا. كاين تبارك الله شي اساتذه الصراحه كيشرحوا واعر وما كياخذوش الحوايج تري سيريو داكشي، واليز حتى هما اللي الاساتذه اللي عزيزين علينا حنا، حيت هما الاساتذه اللي كنفهموا معاه. يلا نبداو الفيديو.
Hello everyone and welcome to this lecture about the difference between classical mechanics and quantum mechanics. I'm so glad to see that so many people showed up today. Anyhow, this lecture will take a while, so let's get comfortable and start with something simple. Now maybe simple like addition and other basic operations. If you take one apple and add another one to it, then you get 2 apples. If you add yet another one, you get 3. If you add another 2, you will get 5, and so on. This is addition, and I will use it as a starting point in order to explain how quantum mechanics works. Because you see, if you take these summed up apples, then you can multiply them together. Multiplication tells you how many times you have to add something together in order to get the multiplied result. For example, you can multiply 5 by 2, or 5 by 4, or 5 by 10, or 5 by 600. The idea is the same. Now next we have exponents, or in other words, the same logic except this time for multiplication. So exponents tell you how many times you have to multiply something. We really often like to use dimensions in order to visualize exponents, but this usually limits us to only 3 powers. Here's an alternative way to think about them. I'll replace apples with icospheres for the sake of rendering all of these animations in just 1 week, because it's gonna be a lot. If you take 5 for example, then bringing it to the 5th power would mean multiplying 1 by 5, then multiplying by 5 a second time, then a third time, then a 4th time, and then finally by 5 the 5th time, which results in 3125, or in other words, quite a lot. Now that we know the basic operations, it's time to talk about... Let's start the simple.
احنا صافي راه في لي رياكسيون اللي قبل فهمنا زعما بالنا فهمنا الاناليز مزيان. دابا داك الماط اللي كنا دوينا عليه داك السيمانه تقريبا نقدر نقول لك شويه لاجيبغ والاناليز فهمتي. هذاك هو الماط اللي فهمنا في لا رياكسيون قبل. هذه كنظن انها باينه. بالنسبه لاديسيون باينه، لاديسيون شي حاجه طبيعيه يعني دغيا تبان لك مثلا هزيتي 5 تفاحات يعني عندك 5. بالنسبه للملتيبليكاسيون راه باينه. هذه اللي ما قلتهاش في لا رياكسيون اللي قبل، ان لو فيت انك كدير الملتيبليكاسيون يعني كتولي عندك واحد السيرفاس. علاش هادشي غادي ينفع؟ هي غادي تبين لك العلاقه تاعها ما بينه وبين لانتيغرال، حيت لانتيغرال في الاخر غير السيرفاس اللي كاين تحت من الكورب. ومن بعد غادي نفهموا مزيان هاد القضيه حيتاش فريمون مهمه. وهنا شرح واحد الحاجه زوينه الصراحه، بحال اذا شديتي 5 يعني عندك واحد اللين يعني 5 على بيسونس 1، درتي 5 على بيسونس 2 يعني خديتي داك السيرفاس اللي هو كاري، سيرفاس تاع واحد الكاري حيت 5 في 5 كتعاود 5 المرات. وعاد عاوتاني اذا درتي 5 على بيسونس 3 راه غادي تولي كوب. صراحه زوينه هذه طريقه التفكير تاعها زوينه باش تفكر بحال هكا تفكر ليكسبونونسيال. غير هو البلان راه حدك 3 حيت حنا كبنادم كنشوفوا الحوايج غير 3 ديمونسيون فيزيكمون. صافي هنا غير بحال بدل طريقه التفكير تاع هذا الكوب وردها غير اكسبونونسيال اللي هو على بيسونس داك الحاجه على بيسونس. هذه هي الاكسبو.
Let's start the simple stuff, like a 1 or a 2 or a 3. If we put all numbers on the line going like this, then we end up with a number line. Now this is incredibly convenient because it allows us to visualize things way more easily. For example, if you start right here with a 4, then you can add 2 to it and move it right. Or you can take 3, for example, and add a 5 to it. Or you can take 1 and add another 1. But one thing which is really interesting is that no matter what you add together, you always move right, never left. So what if you want to move left? Well, let's examine this a bit more closely. Now, it will get a bit cramped, but just stick with me here. We'll start with a blue point, to which we will add a yellow point, and we will get a red point in return. I know it is not as clear as we would all like it to be, but it will have to do. And here's also an arrow which will clear up absolutely nothing. I'll give you a second to take it all in because now it's time for me to move around a bit. So if we move these points around, there is one really interesting thing we can see. The arrow attached to the ball always points to the right, never to the left. So what do we do now? Well, nothing. It seems like it is impossible for us to combine any two numbers and end up with an arrow thus going left. A person would end this argument, but we're not here to be reasonable. We're here to do math. So let's take another closer look at this problem. You see, if we freeze the first point in place and just move around the second one, it would seem like the lower the number gets, the closer the arrow gets to pointing left. So what if, and just hear me out here, what if we were to add an additional number line, this time left from the 0? Well then, if we put the second point onto the other side, congratulations, we got the arrow to point left. Now that's something that really often gets underappreciated, just how weird and bizarre negative numbers are. But that's how these things get done in math, and that's how new math is invented. As long as something works and helps you solve a problem, it doesn't really have to make sense. So let's revise it for a second just to make sure that we all understand how this works. First, we start with the problem. Then, if in our current model there is no way to solve that problem, we have two choices. One, give up and just assume that the problem is impossible, or reinvent the model and add something new that seems ridiculous but in reality could help you solve it. Now, reinventing the model will always seem like absolute nonsense, because what we're basically saying is, hey, remember that math thing that we all did and seems to be working perfectly fine? Well, how about we change it? But it doesn't matter, because feeling of making sense and making sense are two different things, which is a perfect way to segue into the second problem on our list of two problems. Let's imagine that we want to take some number x and square it, and get a negative number in return. How could we achieve that? Well, if you take a closer look at our extended number line, you will see that if we start at the red point and square it in order to get a blue point, no matter where we place the red point, the blue point will always be above 0. Always. So how can we bring the blue point to the negative side? Now, once again, we're faced with the exact same problem. And once again, there is a simple way to fix this problem. Just add more numbers. This time, instead of extending the number line to the left, we'll add another number line, the imaginary number line. So now if you take the I, which is the imaginary number, I mean I stands for imaginary, you get it, I don't know why I feel the need to explain it, and square it, then you will get -1. That's the definition for negative numbers. It's just the square root of -1 is I. That's the entire thing. Yeah, that's the whole definition. I'm glad I have an entire separate chapter just about this. -1 square root. That's cool, great. And there we go. That's the explanation for imaginary numbers. That's the reason behind them. You see, you can have 2 apples or 3 apples. That's basic, that's not that weird. But you can't have -7 or 7 imaginary apples, because these numbers aren't made to represent the quantity of things in real life. They were created to support maths. That's why they exist. Not as the numbers stand alone by themselves, only as mathematical tools to describe other things. And right here is where most imaginary numbers explanations would end. But we can't have that yet, because you see, every single reasonable explanation requires 2 parts. First of all, why something makes sense, and second of all, why it's useful. And so far from what I've shown you, it seems like imaginary numbers, well, kind of make sense, but why would they be useful? Just I times I equals -1? What good does that do? Imaginary numbers are all about rotation. Now, from the explanation I've provided so far, it might seem weird, because the only thing that's defining imaginary numbers is I multiplied by I equals -1. So how could this help us describe rotation? Well, let's bring up our complex plane. That's the real number line and the imaginary number line. Together, they are called a complex plane. I should have mentioned that. And let's start with a 1. Now, let's take a look at what happens when you multiply this 1 by I, the imaginary number. The dot goes from here to here, because 1 multiplied by I is I. Now, let's take I and let's multiply it by another I. We already know that I times I is equal to -1. That's the definition. Now we can multiply it by I and get -1I. And if we multiply that by I yet again, we get -I multiplied by I. Or in other words, we get -1 multiplied by I multiplied by I. Or in other words, we get -1 multiplied by -1. Or in other words, we get a 1. And there we go. We are already rotating it around the origin. But I have something that's even better. Let's imagine an equation like this. E to the power theta I. Yeah, I know, new letter E and fucking Greek alphabet, but it is simple. E is just a number. I could extend it to 2.71828818253602874572497757474709369995. But that unfortunately wouldn't fit in the animation, so I thought that E might be a bit better. But when it comes to theta, the Greek letter, it's just a placeholder. It's meant to be just a character representing a different value. If it's making you uncomfortable, I can just replace it with a smiley face if you want. Now, this equation is wonderful when it comes to explaining how imaginary numbers impact rotations. I'll use this dot right here to represent what this equation is equal to, and also will slowly increase the value of the smiley face. Now, take a look at what happens. We get a perfect circle rotation. That's why imaginary numbers are so important. Without imaginary numbers, you can't describe rotations all that well. With imaginary numbers, you can describe them perfectly. And the thing about maths is, when you unlock a new tool, you not only unlock this tool, you also unlock every single thing connected to this tool. So with imaginary numbers, you can solve not only rotation, but also angles, circles, oscillations, waves, this will be important later, and all the other things derived from those. Take a look at the sine function, for example. Extremely useful, extremely famous, appears everywhere. But if you take a look at its origins, then you will see that it originates from a circle and is used to describe rotation. So where's the I? Well, let me show you something that you might have not seen before. The mathematical definition of sine using just 3 aforementioned basic operations. Or in other words, this. We found the i's. So yes, even though the basic idea for why imaginary numbers exist is, well, basic, it's just I times I equals -1, that's the entire thing, their implementations cannot be underestimated. They are extremely useful.
What the heck؟ ما يمكنش ما تقولش لي هاد الشيء قالوا هاد السيد. ما يمكنش تقول لي هادشي قالوا السيد. واش فهمتوا شنو قال؟ وات لا والله ما يمكن. دابا مشينا صافي بغينا نديكريو الارقام ياك صافي الارقام يمكن حيت حنا بوزيتيف داكشي ساهل دغيا نجبدوا لك بوزيتيف شي حاجه بوزيتيف دغيا نجبدها لك صافي. قلنا هادشي غادي نديرو غادي نحطوا واحد اللين وغادي نحطوا فيها الارقام ماشي شي حاجه فهمتي داكشي اللي دار حط واحد اللين فيها الارقام. وشنو درنا حطينا كل رقم حطيناه في واحد اللين واحد الرقم عنده 1 واحد الرقم عنده 2 واحد الرقم عنده 3. اذا زدتي 1 على 2 كما كتشوف هنايا كتزيد 1 على 2 يعطيك 3 يعني ماشي خيال علمي. واذا لاحظتي ان هذوك الجوج كيديوك هاد الجهه كيديوك جهه واحده ما يمكنش يرجعوا وانت عندك الزائد. المهم حنا بدينا كنزيدو والو ما فهمتي داكشي ما بغاش يرجع بقينا كنخربقوا في الارقام هذه زائد هذه وداكشي ما بغاش يرجع. شنو درنا من بعد صيبنا حيت هذا هو الماط بحال كتقول لغه مثلا هذه باقي ما تصيباتش راه ما غاديش نسميوها قرعه مثلا فهمتي هذه تكون باقي ما صيباتش ولكن تخيل معايا هذه ولات كتبان لينا نقول لهم الدراري شبان لكم فهاد اللعيبه نسميوها قرعه تسميها قرعه انت تسميها قرعه يلا صافي نسميوها قرعه تقد تنفعنا شي نهار اذا كنا ندويو تقد تنفعنا. نفس حاجه بالماط غير بحال بغينا حنا نحلوا واحد المشكله في الماط اللي هي هذه. دابا نورمالمون الحوايج بقيناهم كيمشي من هنا علاش ما نقدوش نلقاو شي حل باش يرجع لنا من هنا. وداكشي اللي دار لنا الماط ها هو شرح دار هذا الموديل يعني ملي كتكون عندك المشكله كيفاش كتحلها زعما هذا التفكير تاع الموديل حيت الهضره اللغه وداكشي كامل سي طا موديل فهمتي. هادشي علاش انا عندي واحد الموديل اللي هو الدارجه واحد اخر عنده الفرنسي اللي ساكن في فرنسا واحد اخر عنده الشينوي اللي ساكن في الشينوا وعنده دي سيمبول تاعو وعنده داكشي تاعو واش فهمتوا يعني غير موديل غير واحد الحاجه باش ديكريلي لك نفس الحاجه خاصنا غير شي حاجه دير لنا التراديكسيون ما بيني وبين هذاك خونا باش نتفقوا على شي هضره مثلا. هادشي نفس الحاجه بالنسبه للماط هو دار هادي ملي كيكون عندك مشكله كتقول واش كاين شي طريقه باش تصولفها اذا كان سير الله يعاونك اذا كان لا اما تقول المشكله امبوسيبل باش تحلها ولا تعاود تصيب واحد الموديل جديد. تي هاد اللعيبه ما يمكنش الصراحه ما يمكنش. المهم هنا فاش بدا كيدوي على ديما العدد اوكاغي ديما يعطيك بوزيتيف يعني فيما حطيتيه ديما غادي يعطيك البوزيتيف. وهنا من جا لو نومبر كومبلكس عاوتاني بغا يحل الحل تاع انا بغيت شي حاجه نضربها اوكاغي ولكن تعطيني شي حاجه نيجاتيف. داكشي اللي دار هو دار لو نومبر هذا اللي ديما كيعطيك بوزيتيف وخصنا يعطينا واحد لو نومبر نيجاتيف وهذاك سميناه ان نومبر ايماجينير غير حنا اخترعناه هادشي اللي سميتو اصلا لو نومبر ايماجينير حيت ما كاينش غير اخترعناه باش يحل لنا واحد المشكله. من بعد شنو دار هاد لو نومبر ايماجينير شنو خلانا نديرو اذا ضربنا 1 على تعطيك اي على كتعطيك واحد النومبر نيجاتيف ناقص 1 هذاك لو نومبر اللي وصلناه غادي نضربوه في غادي يعطيك ناقص هذاك ناقص 1 يعطيك 1. ومن هنا غادي تبان لك انني يمكن ندير دواره ولكن ماشي سهل باش ندير هاد العيب. هنا فين جا الاوليغ يعني كتبان لك طق 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 ولكن هنا فين جا اوليغ عطى واحد العدد اللي كيرد انني نقد نديكري بواحد لونغل سميها اللي بغيتي كما لاحظتي راه دار سمايلي فيس يعني غير موديل ما ديهاش في شنو هو هذاك نورمالمون راه طيطه السامبول غريك هو دار سمايلي فيس تقدر دير اللي بغيتي وهذاك غير اونغل وصافي. ومعك كدير هذاك لونغل حيت انت عندك هذاك لو نومبر اوليغ 2.0 بزاف د الحوايج راه دايره في الفيديو كديكري لك بارفيتمون واحد السيركل. وهنا يعني من لو نومبر يمكن نقول لك حيت السينوس راه الصراحه سي ان فونكسيون اللي كديكري لك الروتاسيون تقدر ديرها في سو فورم ديال واحد الكور، ولكن اذا شتيها هي في الحقيقه راه هي لو نومبر اولير. هذه فونكسيون يعني لو نومبر اولير مضروب في اي، وهذاك الزاد هو اللي كتقول لونغل، يعني على حسب اللونغل شحال يخرج لك هذا السينوس. يعني هذاك لي فونكسيون اللي كيبان لك دابا هو الصراحه شنو كيدير السينوس وشنو كيدير الكوسينوس. الفاريابل هنايا هو الزاد، هو لونغل بالغاديون، لونغل بالغاديون يعني ماشي دوغري، ماشي بالدوغري ولكن بالغاديون، حيت الغاديون هو داك 3.14 اذا كنتي بي، هذا هو لو نومبر بالغاديون. كنتمنى هذا يكون بان حيت فريمون انا ناضي شوف مين كتناضي صافي تفرجوا فيه. انا ما شوف انا بلا ما نتفرج فيه كاع، اذا كنتي كتفهم شويه اللونغلي كتشد كلمه ما كنتش كلمه بحال هكا كسير تفرج فيه فريمون واعر، حيت عنده بزاف الفيديوهات هذا غير بغيت نقرب حيت حنا دزنا من لاديسيون ولينا كنعرفوا لي فريكونس اللي اصلا ديجا كاين في العقل تاعنا، ودابا غادي نفهموا به الكوانتيك من لاديسيون نفهموا الكوانتيك.
So functions. Now for functions, we'll have to start with equations. We are all familiar with some sort of equations. Like for example, 1 plus 1 equals 2. There we go. That's an equation. Or 2 times 3 equals 6. That's also an equation. Or for example, 2y minus 3y minus 2y times squared minus plus y to y divided by 3 multiplied by y. It's easy. Now you may obviously say something like, make it claiming that these equations are easy isn't quite exactly all that accurate. I mean, yeah, the first one, sure, that was easy, but the third one, have you seen the third one? I suppose that's how can that be easy? The third one does seem to be a bit more difficult, but it's not. And in order to understand why, we'll have to talk about toughness versus complexity. Complexity and toughness are two very different terms which people really often tend to mistake. It's not that hard for me to come up with a complex problem and tough problem, but when it comes to solving these problems, for toughness you need intelligence, whilst for complexity you need speed. And that's actually kind of it. Let's take a look back at this equation. It's my very own, extremely old boat-fender equation. If you take a closer look, you'll notice that even though it's not that small, it's easy. Really easy. I mean, addition, division, you could solve it yourself if you want to. Now let's take a look at something that's actually hard. I'm shooting myself in the foot a bit with this, but the Gaussian integral. It's an extremely hard problem. So hard, in fact, I won't be able to explain it here. I'd recommend 3 Blue 1 Brown's video, why pi is in the normal distribution, but you might have seen this animation meme before, showcasing step by step how to solve this integral. But here's the incredibly important, really often overlooked thing when it comes to this integral. This integral is not difficult because it's an integral, it's not difficult because it uses some funky notation, and it is not difficult because it takes a lot of steps in order to solve. No, this integral is difficult because it requires a lot of creativity in order to solve it. Taking the integral, bringing up from 2 dimensions to 3, then switching the coordinates to polar, then treating it like cylinders with the distance, that's creative, that's intelligent, that is new, that's why it's hard. So I guess that would be the main lesson of this video. When it comes to problems, don't judge them by just how large they are or just by how complex they are. No. The only thing that matters when it comes to problems is how difficult they are. And the only way to actually check if a problem is difficult or not for you is to try to solve it. I know it's not all that pleasing of an explanation, but that is the truth. People really often like to use these quantum mechanical equations, like this, for example, will be like, oh my goodness, that's so crazy difficult. But it's not. It's complex. There's just a lot of things going on, and scientists which like to use some notation that looks weird, whilst in reality this is actually pretty simple. So I guess that will be the main point of this video. All of these things aren't that difficult, and if you actually want to explain quantum physics, you can do it in just a single video, from addition to this.
So what is ClickUp? ClickUp is an all-in-one product.
What are you talking about? Oh yeah, right. So let's take this equation for example. The only reason I'm picking this is it has a lot of different operations, so I think that it would be nice. It's 4 plus 3 divided by 2 times 6 squared. Cool. Now, if we change the 4 to 5, then the result changes. That much is obvious. We added 1 to this, so we get a result which is also 1 higher. Simple. Now let's add 1 to this 2 right here. We do it and we get a number that's smaller. That's weird. We added a number, but the result is smaller. We should take a closer look, and for that we should check it for more numbers. We should check what we get for a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, and a... Alright, that's pointless. Too many numbers. We need a different, more graphical approach. Let's go back to our number line and let's add another one. This time it won't be the imaginary axis, only the result axis. So here's how this will work. We'll take 1, for example. We'll take the 1, we will input it right here into the equation, and we will add another dot representing the result. Now we'll repeat this for 2. Take the 2, input it into the equation, and note it down. Now 3, input, result, output. We can keep on going and just adding more numbers. There we go. This shows us pretty well what the function is all about, but if you want this to be even clearer, you can connect the dots. There we go. This graph right here tells you exactly what happens to the equation. And the idea is for each number on the x-axis, you take it, you use it to replace the x in the equation, and you bring it up to the height equal to y. Now, what's really neat is that we can repeat this process for every single number in our equation. And you can see how replacing the 4 with x causes the function to just go up, replacing the 3 causes it to go up in a different way, replacing the 6 changes the shape, and replacing the exponent to does something that's even weirder. So that's what functions are all about telling us how the function changes based on a single number, changing it. And this would actually be a perfect segue for calculus. Here's the thing about math.
فريمون استيدوا على بزاف الحوايج اللي مهمين. بعدا اشرح واحد اللعيبه، اشرح الفرق ما بين شي مشكله اللي كومبلكس، يعني كومبلكس يعني كتحتاج شي حاجه سامبل باش تسولفي شي حاجه كومبلكس، وكومبلكس ماشي يعني صعيبه. كومبلكس يعني كتاخذ هاد الحاجه اللي سهله وكتبقى تعاودها بزاف المرات. اذا كنتي في العالم تاع لي لوجيسيال وداكشي غيبان لك هادشي اللي كيقول راه فغي، حيت دابا لي لوجيسيال بزاف كتبقى تشوف لي لوجيسيال كتقول واه هذا كومبلكس، هاد خونا اللي كيكودي هاد اللوجيسيال ولا اللي كيبروغرامي عنده واحد الذكاء اللي ما يمكنش ولا فهمتي، ولكن هو في الحقيقه غير كيعاود ديك الحاجه السامبل بزاف المرات. وملي كيعاود ديك الحاجه السامبل بزاف المرات هي فاش كتبان انها كومبلكس، يعني كتبان هي صعيبه. تقد شي واحد ما عمرو ما شرحتي ليه البروغرام ولا شي حاجه تقد تبان ليه صعيبه، ولكن شي واحد شرحتي ليه دغيا بروغرام وقلتي هاي هذه حاجه سهله وهذه حاجه سهله وهذه حاجه سهله، كتجمعهم بزاف المرات وكتعاودهم بزاف المرات وكيعطيك هذه الحاجه اللي كومبلكس فهمتي. وعد بين الفرق ما بينه وبين الصعوبه قال لك بحال هذه دابا هذه اذا بغيتي تحلها فريمون خصك دير شي حوايج اللي نورمالمون ماشي سام، حيت تقول لي حقا غادي ناخذ هادي ونفرقها جوج المرات من زيرو بلس لانفيني ومن زيرو موال لانفيني، وكتبقى تدخل وكترومبلاسي داك الكوسينوس والسينوس. الصراحه ما طيحش لك هذه في البال باش تدير ريزوليوشن تاع لانتيغرال. يعني هذه بحال هذه فريمون صعيبه، يعني خصك فريمون تكون واحد الانسان اللي كرياتيف بزاف فهمتي، يعني اللي كيشوف الحاجه بواحد الطريقه اللي في شكل، وهي فاش قد تحل هاد المشكله فهمتي، زعما داك البروبليم اللي فيه لانتيغرال. وبين هاد ليكواسيون صراحه انا نتل دابا ما عرفتش شنو كتحاول تاكسبليكي، يمكن واقيلا الفيتاس واقيلا دي فيتاس. المهم تنشوفوا معاكم هذا شنو كيحاول اكسبليكي. قال لك هذه راه في الصراحه راه سامبل، يعني غير سامبل وكنت كومبليكا، يعني كتاخذ شي حاجه بازيك سامبل وكتعاودها بزاف المرات. هنا فاش عجبتني صراحه الطريقه باش نفهم باش نشرح لي فونكسيون راه كيما بين هنا بالضبط انك كتاخذ غير لي نومبر وكتبقى تفاغيهم وكتختار انت شنو باغي تفاغي. هادشي اللي دار، وكتحطهم في الكوب اذا بغيتي تحطهم في الكوب ماشي مشكل، وكتاخذ كاع لي فالور فهمتي، حيتاش اكس تقد تاخذ من الزيرو حتى بلس لانفيني. اذا خديتي لو نومبر ريال ومن زيرو لموان لانفيني، وتقد تاخذ شحال ما بغيتي بريسيزيون، تقد تاخذ 0.0000001 في بريسيزيون تقد تزيدها، ومن تما غادي تبان لك ان هذاك الفونكسيون راه كتلاقى مع بعضياتها وكتبدل بواحد اللعيبه. يعني بحال كترد هذاك الايكواسيون اللي غير هي نورمالمون غير لي نومبر، كتحط فيها الفاريابل كيتبدل اون فونكسيون تاع مثلا هنا اكس، هنا اكس وهنا الريزولتا، يعني شحال يخرج لك هنايا، وهنا اذا فاريتي الاكس شحال يخرج لك في الريزولتا. يعني هذا هو اذا بغيتي تعطي معنى للفونكسيون. صراحه عجبتني الطريقه. وهنا كل مره حط اكس بلاصه، كل مره هنا فاغيا مثلا هنا كان فاغي هذا العدد، ولكن هنا فاغي عدد واحد اخر، يعني فاغي هذا العدد وهنا غادي فاغي هذا العدد، كل واحد وكيفاش يخرج لك. صافي هادشي اللي دار. صافي دابا ندوزو كالكولس اللي هو الاناليز عندنا حنايا بالفرنسي.
Calculus. Here's the thing about math. If we take a look at this graph, then we clearly can say how things are changing, right? I mean, you can clearly say that over here the function is going up, over here the function is going down, over here it's kind of flatlining, then going down. Yeah, we can say that. But when it comes to math, you really often need a number, a value, something that you can actually check the representation. If it's going up, how much is it going up? How long is it going up? Is it going up forever or will it fall down again? When it comes to math, you need values. You need to be precise. You need to be mathematically precise, or in other words, perfect. Which means right now, we need to find a way to describe this change mathematically. How could we do it? Well, let's first start with slopes. It's just a line at an angle. I feel like that's a solid enough definition for the purposes of this video. So, now, here's what we want to achieve. We want to create a system in which a slope like this would give us a high value, because it's a high slope. A slope like this would give us a low value, because it's a low slope. A slope like this would give us 0, because there is no slope. And a slope like this would give us a negative value, because it goes the other way. So how would we do it? Well, let's start by adding some numbers. We'll start with 2 points, the point A and point B. Both of them would have some coordinates, the x-coordinate and the y-coordinate. I'll just move them around a bit so that everyone would get how they work, because I believe that graphically it makes more sense than explaining it. Now, 4 numbers is a bit much, so we can reduce them down to 2. Because if you think about it, moving points 5 units to the right would result in the same slope as moving both of them 5 units to the left. Which means that we don't really care about their actual positions, only about their relative positions. Or in other words, we only care about how far away this point is from this point. So if we take their coordinates and just subtract them, we get this. And because numbers all by themselves are kind of hard to follow, we can represent this graphically with these 2 lines. Now here's where the fun begins. Because you see, if you increase the height, the slope increases. If you decrease the height, the slope decreases. So that's already half of the equation. What's the other half? Well, that's simple. Width. If we increase the width, we get a lower slope. If we decrease it, we get a higher slope. So what we can do is just inverse it. So divide 1 by width. Now, if we multiply these 2 together, then we get a value which represents the slope. So the slope of any 2 points would be just the difference of their height divided by the difference of their widths. And considering that in this case we have the x-coordinate and y-coordinate, we can note it down as the difference of y divided by the difference of x. So there we go. That is simple. If you have 2 points, then you can check the slope by just dividing this by this. Easy stuff. Except here's the issue. When you're talking about functions, then you're talking about change at a point. Not 2 points, 1 point. which is less. If we're talking about change, we want to talk about change at this exact spot, not the spot next to it, not the spot behind it, only this exact spot, which brings us to a problem. How could we describe this with only one point? Well, that's actually extremely easy. All you have to do is just bring back the distance from this distance down to 0. Now the 2 points are actually overlapping, and it's not an illusion, they actually are overlapping. If you bring down the distance to 0, they actually are, 2 points are in the exact same spot. Mathematically, it's accurate, it's fine, it's perfect. The only issue is if the distance between them is 0, then you end up with 0 divided by 0. How do you solve that? Well, let's take a closer look at what we're basically doing over here. Since we define slope as the difference between 2 points, we start that definition. We reduce the number of points to 1, and then we calculate. But here's the thing, what if we try to do it the other way around? In order to get what that means, let's try it with an example. First, we'll consider a function. F of x is equal to x squared. Now, let's try it the flawed way first. So we start the point, let's say, for example, something like this one right here. Now, what are the coordinates of this point? Well, the x, or the width, will be equal to x, and the y will be equal to the height. So x upward to the function. So far, all of this is not all that complex, but I still would like to pause to make sure that it all makes sense. Alright, we have this point, which has coordinates of x and y. X is equal to x, and y is equal to f of x. Cool. Now what about this other point? Well, the other point we can just define by an offset. And even though it sounds fancy, it just means that it will be an h further away than this point, and f of x plus h higher than this point. Now, what is the slope created by these 2 points? Well, once again, the difference of heights divided by the difference of widths. There we go. That's the equation. Now we go to the second thing on our list, which is to reduce the 2 points into 1 point. The way to do it would be by replacing the h with 0. So after we replace h with 0, we get... we get f of x minus f of x divided by 0, or in other words, 0 divided by 0. Once again, we have the same problem. That's why we need to be smart about this. That's why we'll have to rewind and try this again, but in a different way. Which means that we'll have to leave merging these points for later. For now, let's try to solve this. So f of x is equal to x squared, which means that we can replace these functions with what they mean, like this. Now next, we can try to simplify this a bit. So x plus h squared will be equal to x plus h times x plus h. So we multiply x by x by h by x, and h by h. In the end, we'll end up with this. Now, in this equation, we have x squared and negative x squared, so we can cancel them both out. Now we just end up with xh, xh, and h squared. xh plus xh is equal to 2xh, and now we just need to divide all of them by h. There we go. We end up with 2x plus h. Now, after all calculations are said and done, what is h equal to? Well, obviously it's equal to 0, because once again, we reduce 2 points to 1. So we replace h with 0 and we get 2x. So in this entire function, we can say with absolute certainty that at any point, slope is equal to 2x. But what does this mean exactly? Well, let's start on the left, right here. Here we can see that the function is going down, which means that the slope should be negative. And after we input the x, so negative 2.5, into the equation we get negative 5. Which means that at this very point, the function is going down at a slope of negative 5. If we move it to the right a bit, we can see that the function is still going down, but not as much. So if we once again input the x into the equation, we get negative 0.5. So still going down, but less than previously. Now right here, x is equal to 0. 0 times 2 is still 0, so the slope is not existent. And we can see that right here it seems to be rather flat. Now on the positive side, the slope slowly rises. Now this, the function describing slope of a different function, is called derivative. And we use the dy divided by dx notation to note it down. So dy divided by dx of f of x is just the derivative of function f of x. So derivative of x squared is equal to 2x. And this way we can calculate instantaneous slope of any function and precisely describe just how much they are going up and down. Or in other words, just how much the function is changing. That's what I adore about calculus. And here's the thing, if you understand what I've said so far, then you pretty much understand the whole calculus. There's only one more thing left to mention, which is this, the integral. Integral has a reputation for being incredibly difficult, but in reality the concept is unbelievably simple. Take a look at this function. You want to know what the integral of this function would be equal to? The area. That is it. That's the entire thing. That's what the integral is. But what if you want to actually calculate this integral? Well then, all you have to do is, remember taking the derivative, the thing I just mentioned from the function, the derivative? Well, if you go back, then that's just taking the integral. If you understand derivatives, then you also understand integrals. Many people even often refer to integrals as anti-derivation, because it's just derivation going the other way. I think that sucks, actually. I think the integrals should be called integrals and the derivatives should be called disintegration, but that's just me. I stole that joke, by the way. Now, I feel like there's still one. I think that sucks, actually. I think the integrals should be called integrals and the derivatives should be called disintegration, but that's just me. I stole that joke, by the way. Now, I feel like there is still one more question to be answered when it comes to calculus, and that's, why would we ever need to know the exact slope at a single point? Well, let's consider an example like this. You have a car which is traveling with some velocity. How would we calculate this velocity? Well, normally the answer would be simple. Take the distance this car has traveled and divide it by the time it took it to travel. In this case, if, let's say, this car has traveled 16 meters in 4 seconds, then we know that the velocity is equal to 16 meters per 4 seconds. Or in other words, 4 meters per second. That's how we usually do it in classical mechanics. Why do I say usually? Well, it's because, as with everything, there is an asterisk, because this is not equal to the velocity. This is equal to the average velocity. What about the actual velocity at any moment? Well, let's rewind to the very beginning and let's stop the car mid-track. How quickly is it going at 2 seconds? In the exact instant 2 seconds have passed. Well, that's simple. After 2 seconds, in that instant, the car has traveled 0 meters in 0 seconds. I mean, we're talking about an instant, right? An instant. That's what an instant is. 0 seconds. So obviously the car has traveled 0 meters. It's an instant. Once again, we're faced with the exact same problem. And the way to solve it is with the derivative. That's what the derivative is. A change of y in relation to x. And that's what velocity is. A derivative of position in relation to time. Meters, so position, in relation to time, so seconds. Derivation is actually an extremely common operation. The problem is, it's a bit too common, don't you think? I mean, if you use derivation to calculate something as simple as velocity, then how is it possible that most people have never heard of it? Well, it's because of precision. The difference between velocity and average velocity is that whilst average velocity is imperfect, because it obviously gives you the average velocity over the period of time, it is easier to calculate. Derivatives are harder to calculate, and that's why most people don't use them, even though they give you the perfectly exact velocity at any point. This difficulty with precision increase will come up soon, but first... And so there we go, that was calculus explained in... I have no idea, I haven't edited yet. Now it's time for the last bit before quantum physics.
اوكي نشرح القضيه كما خاصها تشرح. كما لاحظتي ان صافي عندك واحد الفونكسيون، صايبنا واحد الفونكسيون ما همناش حنايا ياك، ولكن دابا حنايا بغينا نعرفوا بالضبط في واحد لو بوين شحال غادي نطلعوا شحال نهبطوا. انا كيفاش كنتخيلها بحال انت في الطوموبيله مثلا عندك انت تطلع مثلا شي طلعه ولا تهبط النزله ولا انت في واحد الجهه اللي فلات. انا بحال هكا كيفاش كنتخيلها، يعني داك تي طالع، يعني طبيعه الحال الديريفي تكون طالعه ياك، تبقى طالع 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 ومثلا وصلت واحد الجهه الفلات، يعني الديريفي ما كايناش تساوي زيرو. علاش؟ حيتاش ما كاينه انت ما هابط ما طالع، فهمتي؟ علاش كتساوي زيرو، ومثلا داك تي هابط راه الديريفي غادي يكون نيجاتيف. هي هذه دابا شنو بالضبط شنو غايدير لك الديريفي؟ بطبيعه الحال غادي يديكريلي لك غير الفونكسيون امتى تطلع امتى تنزل امتى تهبط. بحال انا في بلاصه ما نقول لك شوف راه طلعات في اكس، طلعت في هاد الجهه وهبطات في هاد الجهه وهادشي كامل باش نقولها ماتيماتيكمون في المات كتولي كتحتاج لا بريسيزيون. مثلا نقول لك انا في هاد النقطه بالضبط قول لي شحال نطلع وشحال ننزل، وهادشي اللي دار لك الديريفي. دابا نورمالمون راه هادي كانت واحد المشكله عندنا، اننا باش نعرفوا سلوب تاع واحد النقطه سبيسيفيك قلنا صعيبه، قلنا خصنا على الاقل جوج لي بوين باش نعرفوا واش طالعين ولا نازلين ولا حنا في بلاصه. غير هو شنو درنا حنايا؟ حسبنا جوج لي بوين من بعد جمعناهم في بوين وحده، وهنا ملي غتحسب هادشي كامل غادي يعطيك ان هذا مثلا اذا خديتي اكس او كاري، اذا عرفتي الديريفي تاع اكس او كاري هي 2 اكس وزائد اش هو شحال فاريتي داك الفونكسيون، شنو هو لا ديستونس ما بين هادوك لي دو بوين. طبيعه الحال كل ما كانت لا ديستونس قريبه كل ما كانت الديريفي صحيحه عندك، وامتى تكون الديريفي 100% صحيحه يعني ايديالمون هو اذا كان كيساوي زيرو. وداكشي اللي درنا حنا في الاول كالكولينا السلوب، خدينا دو بوين قراب من بعضياتهم، من بعد هو غوبلاسينا داك بلس اش هذاك لو با بزيرو، وهنا فاش تعطيك 2 اكس يعني الديريفي تاع اكس او كاري يعطيك 2 اكس. وتقريبا هي هادشي علاش انا وتهاد خونا كيبان ليه ان خاصك تفهم مزيان لا ديفيزيون، تفهم الملتيبليكاسيون، تفهم السوستراكسيون. صافي هادشي اللي محتاج انت باش تفهم الماط كامل. ياك فهمتي الملتيبليكاسيون، فهمتي لا ديفيزيون، لاديسيون، سوستراكسيون، صافي فهمتي الماط كامل. بحال مثلا انت عندك لي فوايال، عندك ا بي سي دي او وكتعرف تقول با بي بو ياك، اون فوا تعرف هادشي صافي تعرف الدوي. انا بحال هكا كنشوف الماط تا هو كنشوفو غير بحال لونغاج، فهمتي؟ يعني اون فوا غادي تعرف تقول بابوبي صافي غتولي تاكسبريمي، غادي تولي تهضر على شي مواضيع وغادي تمشي بعيد وانت غير في بلاصتك، وغادي تدوي على شي حاجات وتفكر بزاف وداكشي كامل. هادشي كامل علاش؟ حيت كتعرف تقول بابوبي. نفس الحاجه بالنسبه للماط، اذا فهمتي بلس موان ناقص داكشي اللي ساهل اللي كلشي فاهمو صافي لاناليز تفهمو. حيت لاناليز غير خدينا هادي وهادي، يعني هادشي كامل اللي قلنا لكم في الفونكسيون كما شرحنا قبل راه غير في بلاصه ما كدوي لو نومبر كتولي لي فاريابل. صافي هذه هي الفونكسيون. صافي هنا شرح لانتيغرال. هادشي علاش قلت لكم قبيله انا خصك تفهم ان الملتيبليكاسيون هي كتعطيك السيرفاس، حيتاش لانتيغرال راه اصلا هي غير السيرفاس اللي كاينه تحت من الفونكسيون. وصافي وانت كيفاش تعرف؟ خاصك دي 2 اكس، يعني خاصك تاخذ شويه تاع دي 2 اكس وغادي تضربها في لا فونكسيون باش تعطيك السيرفاس. ياك هذه هي السيرفاس. غتاخذ دي 2 اكس اللي هو اصلا غير بوين وحده، ولكن نورمالمون راه 2 بوين وحنا رديناه بزز 1 بوين باش يعطينا لانتيغرال فري، فهمتي؟ اما هو نورمالمون راه 2 بوين ديريفي نورمالمون هي كتاخذ 2 بوين تاع شحال هذاك طالع ولا نازل. بحال درتي هنا واحد الخط، بقيتي كدير خطوطه 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 حتى ولا عندك واحد السيرفاس. صافي هذا هو لانتيغرال، هو السيرفاس اللي كاين تحت من الفونكسيون. هنا شرح واحد الحاجه اللي الصراحه خاصها تشرح، هي لو فيت ان الفيتاس راه كاين جوج انواع تاع الفيتاس. كاين هذاك الفيتاس موين اللي ساهله اللي كتبان لك في الطوموبيل، ان الطوموبيله كتمشي 20 متر بار سكوند ولا 20 كيلومتر في الساعه ولا شي حاجه بحال هكا. وعندك لا فيتاس انستونطاني. لا فيتاس انستونطاني راه خصك ديريفي باش تعرف لا فيتيس انستونطاني، حيت الفيتيس شي حاجه لي ديناميك كتبدل، والفيتيس الموين غير كتحسب هذاك الفيتيس عندك كامل وكتاخذ الموين تاعو. الموين غالبا كيكون في الوسط تاع لا فونكسيون تاع الفيتيس. ما عرفتش هادي نكون شرحتها مزيان، مي راه نفس البرانسيپ، غير كتاخذ شحال من متر ضربتي وشحال من سكوند، ولكن في بلاصه ما تاخذ شحال من متر وشحال من سكوند كتاخذ واحد لابارتي من المتر وواحد لابارتي صغيره من السكوند. هادشي علاش دي دو اكس على دي دو دي، وهما راه نقطه، راه مشكله هذه، هما راه غير نقطه ولكن قيسها فيلم. فهمتي؟ فريمون السيد شرح هاد الشيء مزيان. انا بعدا جاني بحال هكا احسن من انا كاع نحاول نشرحو. وعلاش حنا كنديرو فيتاس افريج؟ حيت ساهله باش تقول لي 1 متر بار سكوند على تحسب ليا شحال كيتبدل فريمون لا فيتاس راه فاريابل، كتزيد فيتاس كتنقص فيتاس المهم فهمتي بحال هكا الفيتاس. ولكن حنا كنقولوا كناخذوها الفيتاس موين اللي هي دلتا اكس على دلتا تي. دابا ندوزو probability.
So, where should we begin? How about with the probability function? Let's imagine that we have a basketball and a basket, and we will throw the basketball forward with some random force. Now here's the question. What's the probability that the basketball will make it into the basket? If we throw the basketball with too little force, then we will miss. But give it too much juice and the ball goes flying. So what is the probability that the ball will make it in based on the force? Well, here's the thing. Because of turbulent flow of air, even if you were to throw the ball with the exact same force, it can sometimes go in and sometimes miss the shot. So here's what we can do. For each different force, we can sample different throws and get the probability that the ball will make it in. So for example, if you throw the ball really, really weak, it never goes in. If you throw it a bit stronger, it sometimes goes in, but mostly fails. If you throw it even stronger, it goes in more often. Throw it even stronger and almost always goes in. But be careful, go over the limit, and the ball will mostly fail. Now, based on these different measurements, we can create this. A function which tells us the probability that the ball will make it in, based on the force of the throw. Now, I know that this might have been a lot, but that's the idea. This tells us the strength, and this tells us the success rate. Alright? Simple enough for now. So, we know that if we throw the ball with this force, this is the probability that it will make it in. If we throw it with this force, this is the probability that it will go in. And for this force, this is the probability. Simple enough. But here's the more fun question. Let's say that we pick a random force between here and here, just any random value. What is the new probability that will make it in if we pick a random value for the force? That's a rather difficult question, so let's start with something easier. Let's say that we have only two possible scenarios. We either throw it with 1/3 of the maximum force or 2/3 of the maximum force. Now, if for 1/3 it will have a 25% chance and for 2/3 it will have a 32% chance, then if we pick these values at random, the total probability that the ball will make it in will be equal to 28.5%. Why? Well, it's because there are two possibilities. We have a 50-50% chance that we pick the first one and the 50% chance that we pick the second one. So the total probability is 50% chance that we have a 25% chance probability and 50% chance that will have a 32% chance. So the total is equal to 28.5%. I know that it might have been a bit confusing, so once again, these 0.5s are here because we pick the force at random, either the first force or the second force. It's a 50-50. And then these forces have their own corresponding probability that the ball will make it in. Does that make sense now? No? Well, don't worry, because there is more examples to not make sense. Like, let's expand ours by adding one more possibility. So right now we have three possibilities. We can throw it with 1/4 of the force, 2/4, and 3/4. Now, each of these forces have their very own probability of the ball making it in. For the first one, it's 12%, for the second, it's a 50%, and for the third one, it's 17%. Now, what's the total probability of the ball making it in after we pick one of these three forces at random? Boy, that's a mouthful. Well, each of these forces has a 33% probability of getting picked. So, once again, we multiply these 33% by their corresponding probabilities, then we get 26%. That's the probability that the ball will make it in after we pick one of these three forces at random. Still, let's go once more, this time with 4 forces. We pick a random force, which means that each one of them has a 25% chance of getting picked. Now, here are the probabilities, and by now, you know the drill. Add them up, and we get 24.5%. Now, this process should make some more sense, or at least I hope so, because here's where it gets beautiful. Let's think about what all of this means graphically. In order to make it easier for the eyes, we'll roll back the example to the one with only 3. So we basically sum together the probability of each force getting picked by the probability of the ball going in. Now, what are these two values graphically? Well, the probability of the ball going in is just literally the height of the rectangle. That's simple enough because the function in the background is literally the function in which the height represents probability. So obviously, the height represents probability. Alright, one half of the puzzle solved. Now, what is the probability of each force getting picked? This one is also simple enough. You see, the probability of any force getting picked is equal to 100%, because one force is always picked. Now, if all of them are equally probable, that means that each force has a probability of getting picked equal to 1 divided by the number of segments, which, as it just so happens, is exactly equal to the width of each rectangle. So that means that we can just replace this with height, which, as you remember, is equal to the function in the background. The width we can just replace with 1 divided by number of segments. I'll just note the number of segments down as n. There we go. Now there's one more thing we can do to clean this up, and that's to replace these sums with a single sum. Now, mathematically, this changes nothing. I cannot stress the nothing of it enough. It's only notation. It's just really often used in order to shorten the equation a bit, because if we go back to 4, this is shorter and more readable than this. So yeah, there we go. We made an equation, and one thing that's actually kind of cool is that with this equation we can just slowly increase the number of segments from 4 to 5 to 6 to 7, 8, 9, 10, and so on. And at some point we'll reach the exact area under the function. One pickle though, at what point will we reach this area? Well, that's the issue. We'll reach it only when the number of segments is infinite. Otherwise, if it's equal to something like 1,000, like in this case, we could always just zoom in and see the error. But if it's equal to infinity, it would truly be perfect. That's nice. One little problem, you see, a funny story. If you insert infinity into our equation, then we get 1 divided by infinity. Now, this all by itself is not that big of a problem as it seems. I mean, using just one quick limit, we can say that it approaches 0 with no paradoxes, well, relatively no paradoxes. But if it does actually approach 0, then after we multiply the result of the function by the 0, we get a 0. Which means that this sum is just equal to 0 plus 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 0 and so on, infinite number of times. So how could we solve this problem? Well, we already have. Because we already end up with one paradoxical dead end like this before in the video. Remember derivatives? Over there we also had to divide 0 by 0. So in order to avoid a paradox, we instead divided dy by dx and just sidestepped the whole 0 problem. So what if we do the same thing here? And we say that instead of multiplying by 0, we multiply it by dx, which approaches 0, because width of these segments gets smaller and smaller. And there we go! We have a foolproof equation. Well, almost, because you see, in reality, in this case, we wouldn't really use the capital sigma notation because we don't really know exactly how many things we want to add. I mean, it's approaching infinity, so we don't know the exact number. So instead of sigma, we'll probably use something different like this kind of funky curvy line. Basically, oh my goodness, that's an integral! And so there we go. That's how integrals are made. When a daddy integral and a mommy integral love each other very much, then what they... Okay, I'm sorry. I'm just really excited because if you understood at least most of what I said so far, that means that you just went from addition to calculus in 42 minutes. A journey which normally takes around 16 years. But yeah, calculus, probability, was kind of the last thing on our to-do list. So right now, you do actually understand everything. We went over basic operations, over basic numbers, over advanced numbers, over equations, over functions, over calculus, derivatives and integrals, over probability, which means now it is finally time to get to the last bit of this video. There we go. Now you should understand everything you need to understand in order to get into quantum mechanics. Now obviously I will not explain the whole field, that's way above my pay grade, but I will give you a sample of what it feels like to work with quantum mechanics, and this sample will look like this. Now, isn't that just a beautiful equation? It looks so advanced, so sci-fi. It looks like something that a main character in a movie would try to solve in order to crack time travel. But in reality, as you will soon realize, this equation would be way more familiar to you than you think, except it has a quantum mechanical twist to it. So, without any further ado, let's get into it. Starting with this, psi. That's the name of this symbol, psi. But in reality, the name of this thing in quantum mechanics is the wave function. Now, let's divide into two parts, wave and function. You are already familiar with functions and how they work, what they are. And this is just any normal old function. Yeah, I know, the notation would seem to suggest that it's some sort of bizarre craft, but no, just any normal function. It's just this. It's the exact same thing. Except quantum mechanics really likes to use this all very seemingly advanced notation. But yeah, that's all it is. Psi would be equal to just any function, right? Nothing weird going on there. Except for the return. Because you see, this function, whilst it does take in just any odd number, it returns a complex number. A complex number would be basically a plus bi. Now in this case, a and b are just random numbers, but I is the imaginary number, the number you know pretty well. Now why is this called a complex number? Well, remember the complex plane. Well, if you take this complex number and you were to try to put it on a complex plane, then these are just the coordinates. I mean, a would tell you how much to the right or the left you have to go, and bi would tell you how much up and down you would have to go. Because, you know, if you multiply something by I, then you go up or down. That's just it. So this complex number is just the real number summed up with some imaginary number. But why are we using a complex number instead of just any random normal number? Well, it's because of the first part of this name, wave. It's a wave function. And if you recall me explaining imaginary numbers, then you'll remember how I mentioned that imaginary numbers help you solve angles, circles, and also waves. The reason for why we use imaginary numbers for waves is, well, let's just say that it would make this video about an hour longer, and I will make a whole separate video just about that. But that's all you have to remember for now. This function has to do with waves, and because of that, we need imaginary numbers in order to describe them. So, let's recap. When it comes to this, it's just a function which takes in a number
and returns a complex number, or in other words, a real number and an imaginary number. I know it's a lot, but it should make sense if you just stop and think about it. So let's go on, and let's add this. An asterisk and another psi. What is this asterisk? Well, it's not convolution. It is a complex conjugate. Oh my goodness, it sounds amazing, doesn't it? Complex conjugate. So sci-fi again. But in reality, as always, it is incredibly simple. You see, what a complex conjugate does, it just takes the complex number and just flips the imaginary part. That is it. So remember when you had a plus bi? Well, if you take a complex conjugate of it, you get a minus bi. That is it. That's all complex conjugate does. It just flips the imaginary part from positive to negative. So, what does psi, complex conjugate of psi, give us? Why is that there? Well, let's see what happens if we do actually apply this. By the way, this is psi multiplied by the complex conjugate of psi. I should have mentioned that. Let's see what happens when we actually solve this equation. Well, psi gives us a plus bi. We already remember that. So, let's multiply a plus bi by, in brackets, a minus bi. What do we get? Well, first, a times a gives us a squared. Then a times bi gives us abi, and then bi, but that's with a negative, so minus abi. Then we have bi times a, which gives us once again abi, this time is positive, and then we have I multiplied by negative I. That's the last thing. So we have a squared minus abi plus abi, which means these two cancel each other out. And then what we have is negative I squared, negative bi squared. I'm doing this from memory, alright? Now, what is negative bi squared? Well, let's think about it. What is I squared? Well, if you remember it from the definition, I times I equals negative 1, which means I squared in this case will be just negative 1. So we have negative 1 times b. Negatives cancel each other out, and because of that we just get plus b squared. A squared plus b squared. Now, this may seem just extremely convoluted for absolutely no reason, but there is a reason. You see, on the beginning, from our psi function, we got a complex number, so a real number and an imaginary number. Now, after performing this operation, we get two squares of real numbers, or in other words, a positive number. So even though these functions can output any number in existence, positive, negative, imaginary, real, any number, after we apply a multiplication by complex conjugate, we get a positive number, a real positive number every single time. I'll leave it up on the screen for a second just so that you can actually take all of this in. Alright, everything clear? No? Well, then I will suggest rewinding, because here we get into fun stuff, because here we get into probability. Why do we care about this function returning a positive number? Well, it's because you can't work with probability with negative numbers. You can't have negative probability. And so here's the thing. After we take psi, complex conjugate, psi, what we get is the probability function. Probability function of what? Well, a probability function of finding an atom in any place. Well, not an atom, a particle. So here's the idea. You take this function for any particle and you input a position into it. And then this function tells you what is the probability of this particle being in that position. That's already extremely useful. But once again, let's take it all in, alright? You give this function a position and it returns a probability of a particle being in that position. Okay, so if we imagine a line, and then we can assume that particle can be anywhere on that line. So if we want to figure out where the particle is, then we sample this position, we input into the equation, and we check, oh my goodness, the particle has a 25% chance of being in that position. We take another one, we once again do this exact same thing, and we see, oh my goodness, the particle has a 33% chance of being in that position. We sample another position, we input into the function, we get the output, and wow, the particle has a 10% chance of being in that position. That's how it works. Once again, we can connect the line, just like in the probability segment, and get this, the function describing the probability of being in any single place. Now, this all by itself is decently useful, because you can just take a position, input into the function, get the probability. But most of the time, we don't care about the probability of finding particle in any place. We most of the time care about finding the particle in between two places. Because, well, a single spot is not something you would normally do in physics. Normally you would prefer finding particle between point A and point B. And if we rewind back to the probability segment, then you should know that the probability of finding the particle in between point A and point B would be just the area under the function in between point A and point B. That's probability. And oh boy, what is the operation that gives you the area under the function in between point A and point B? Well, that would be the integral. There we go. So we add in the integral to it, and we get an integral of psi complex conjugate psi dx. We're getting into the good stuff, because now we have to add an x to the mix. Why do we add an x? Well, this is actually one thing I haven't explained from probability, because it's just straight up too simple and too short to deserve an explanation. When we have this probability distribution, we have the area under it. If we add x into that spot, then what we get is we get the expected value. We just get the expected value from this probability. So if you actually input the x in there, what you get in return is the expected position of the particle. So if you were to sample this function over and over and over again, this would be the position that you would expect the particle to be. Okay? Now here's the thing. I know this is extremely complex. I know this is extremely difficult. I know there's a lot of things going on, a lot of operations, but we already achieved a pretty interesting result. Because what we got is the expected position of a particle, which is the quantum mechanical version of standard position. Yeah, that's the main difference between classical and quantum mechanics. In classical mechanics, when you have an object, you have the position of that object. So, you have a ball, and then you have the exact position of that ball. You can say that the ball is 2 meters away from you, or 1 meter away from you, or maybe 1 meter to the left, 1 meter to the right. In quantum mechanics, you can't have that. The uncertainty principle disallows that, which basically means that you cannot have an exact position of something. Instead, the position is dependent on the probability, is dependent on the function describing the probability, and because of that, instead of working with values, we work with functions. Functions like these. So, there we go. Instead of position, we have this. Now, why do we have on the beginning of our example equation a derivative? D of x divided by d of t. Well, you should already be familiar with that very derivative, because we, once again, already made it once in this video. This derivative is just velocity. X is position, t is time. This is just position divided by time, or in other words, velocity. And that's what I find so amazing about classical mechanics versus quantum mechanics. Because even though these two things seem so much different, in reality, they're actually kind of the same thing. Not kind of, only exactly the same thing. The only difference is that in quantum mechanics, first of all, you don't work with values, only with functions, and second of all, you have to be way more precise. And because of that, you cannot really shorten your notation, because if we were to actually expand notation, then we should also use derivatives in classical mechanics. But in classical mechanics, it doesn't matter. Things are so large that you don't have to be really all that precise. So whenever people talk about quantum mechanics, about how complex it is, all you have to remember is that it works based on the same underlying rules as classical mechanics. It's very similar. It's still physics, right? It's still the same universe, same laws apply. The only difference is that you work with objects that are so small that you no longer can average the random outputs. You can no longer just average the noisiness. In real life, if the position of an object fluctuates by 1 nanometer, it's not that important. But in quantum mechanics, it is. That's why you can't afford to bind anything to a single value. You have to bind it to probability. You have to be precise. You can't just divide two numbers, you have to use derivatives. You have to make sure that the things do actually make sense, because otherwise, you will not even end up with a number that doesn't make any sense. You will end up with an entire equation that's just too large for quantum. And so there we go. That's what quantum mechanics is all about. I know that it's still pretty complicated, it's still pretty complex, and I haven't explained it perfectly, but all I wanted to show you is that even though the notation is scary, the idea behind it isn't. This is just velocity. As scary and terrifying as it looks, it's just velocity. And that is it. And there we go. In a little bit of an hour, we went from addition to quantum mechanics.
حيتاش في الحقيقة داكشي اللي صغير من كثرة ما صغير، إذا قلت لك أنا لا بوزيسيون كاينة بالضبط هنايا غنكون خاطئ، حيتاش هو صغير بواحد الدرجة اللي ما يمكنش. واش فهمتي؟ يعني خصني نقول لك غادي يكون غير في هاد الجهة هكا، غادي نكون بحال هكاك بريسي كيما بغيت، فهمتي؟ غادي تكون لا بريسيزيون داكشي اللي بغينا. وهنا علاش كندخل البروبابيليتي في لا بوزيسيون، يعني هادشي علاش كاين هاد الفيلم كامل، هادشي كامل زعما غير باش ديكري لا بوزيسيون، حيت ميكانيكمون في الميكانيك بوزيسيون غادي تاخذ مثلا الوسط تاع هذا وتعطيه واحد البوزيسيون، انت تقدر تختار اللي بغيتي. كاين اللي كيختار لو بوين دو ماس، تقدر تختار هذا هو البوزيسيون، المهم انت تختار اللي بغيتي. المهم هذا غادي يعطيك البوزيسيون، واذا حركت هذا واحد نانومتر ما غاديش يبان، ماشي بحال شي حاجه صغيره. واحد نانومتر بحال قلتي صافراش، بحال مشات من تما لتما، فهمتي؟ يعني ما يمكنش انا نقول لك بوزيسيون راه كاينه هنا وهي كاينه تما. واش فهمتي؟ حيت انت صغير بواحد الدرجه اللي ما يمكنش، وواحد نانومتر تاع البريسيزيون صعيب باش تقول فين كاينه. المهم هذا راه شرح غير الويف. نورمالمون الويف راه يمكن لي زوند يمكن تكريهم بلو نومبر كومبلكس، وحنا ضربناها مع بعضياتها، درنا الكونجيغي غير باش يعطينا لا بروبابيليتي. وهاد البروبابيليتي راه نورمالمون كنغميوها، يعني باش تولي تساوي اما تعطيك 0 ولا 100%. اذا لاحظتي راه بروبابيليتي ما كايناش لتحت، كاينها الفوق، يعني من 0 ل 100%. 0 100% يعني السيرفاس، في السيرفاس تاع هاد الفونكسيون دونت. كنتمنى انا الفيديو فهمتوا شي حاجات فيه. اذا ما فهمتوش غالبا انا مع الوقت نحاول انا نأوغمونطي وناميليوري الكومونيكاسيون، كيفاش كنكومونيكي هاد اللعيبات بواحد الطريقه اللي سهله كلشي يفهمها، حيت هو هادشي الصراحه ليدي تاعو ساهل. كتبقى المشكله غير في النوطاسيون. بحال مثلا اللغه، شي مرات عندك مثلا عقلك كيعطيك واحد لي سينيال وانت عارف بالضبط هذوك لي سينيال، ولكن لو فات انك تمشي تحولها هضره يفهمها الاخر، يفهمها كلشي. هنا فين كاين الصعوبه، وهادشي اللي كاين في هادشي تقريبا. يعني تقد تبان لك شي حاجه، ولكن باش تردها سو فورم ماتيماتيك خاصك دوز من هاد لي سيمبول وتزيد لي سيمبول اذا ما كانوش، كتكون من تما كيولي الحوايج شويه صعب. تفرجوا في خونا سميتو ميكتش، راه عنده بزاف الفيديوهات، كيلوح فريمون بزاف الفيديوهات. بطبيعه الحال هادشي اذا كان عندك مع اللونجلي شويه، حيت هو كيدوي 100% غير باللونجلي. وصافي هادشي اللي كاين. نتلاقاو رياكسيون الجايه. باي باي.
يلا مع السلامه. يا بنت قدام المدرسه المديره هتطرد، يخص وقته ده.